We're going to talk today about integration for physics. This is not a calculus class, but we use the tools of calculus to help us solve problems. Most of you have already had calculus a little bit, like in AMA, a little bit of integration at the end. If you're in AB or BC for the first time this year, this will really help you in your AP calc classes because you're going to be doing this. And I take a very conceptual approach to integration. And we're going to, I don't tell you exactly how all the integration rules are derived. You'll do that in your calculus class. I'm going to tell you what calculus is, then I'm going to show you the rules on how to take the integral of different kinds of formulas, but I'm not going to prove that these rules work. Do that in your calculus class.
Yeah. Do you use any special color? Do you assign any special meaning to text in blue and above?
Yeah. No, I don't know.
You don't?
No. So anyway, integration for physics. Let's begin. Well, first of all, we started this last time. I mean, we talked about what if I went, if I was walking. I'm going for a walk, and I'm walking at 2 meters per second, and I walk for, let's say, 5 seconds at 2 meters per second, right? Pretty easy. And by the way, if you see me walking across campus, that's about my walking pace. When I'm walking fast, you know, people make fun of the way I walk, especially Mrs. Heimerdinger. She makes fun of the way I walk. But I walk really fast. I got places to go, and I'm kind of tall and gawky, and so I kind of lean forward in a funny way just so I don't fall down, all right, while I walk. And but I walk at about 2 meters per second. So if I were to graph that, okay, so this is velocity in meters per second, and this is time in seconds. So I go 1, 2 meters per second, and I go 1, 2, 3, 4, 5. And it's kind of silly to do this, but okay, we're going to do it anyway. So my velocity is constant, what means my velocity is not changing with time. And so, and what it means is that every second that goes by, I change my position, I move 2 meters, right, from where I was before. And you can represent that easily by looking at the area underneath the graph. The area underneath the graph. And each one of these little squares here represents a meter of displacement. And because, look, if I were to draw it over here, I would say, hey, this has a height of 1 meter per second and a width of 1 second. And again, this should not be all that freaky. Look, we're using a length to represent time. We're using another length to represent velocity. So it shouldn't be surprising that the area doesn't represent area. I mean, it represents something else. It represents 1 times 1 is 1, and then a meter per second times second is 1 meter of displacement. Am I on screen still? Yes. Is that too small for you in the back? Am I okay? A little small? Okay. Again, move up forward if you need to see. Now, so this is a profound idea that if I have two quantities that I can do this right here. Now, and find the area. Now, look, we have an equation that relates velocity and displacement. That's that second equation, right? Second kinematic equation, delta x equals v plus v naught over 2 times time, right? That's what we just developed with our kinematic equations. Now, is it okay to use this equation? Yes, because the acceleration is constant for this time interval. What is the acceleration? Nope. The acceleration is 0, and it stays 0. So yeah, it's okay. So what's true about the velocity and the initial velocity. What's the velocity? Let's plug in our numbers here. Okay. You can say, well, this is 2 plus 2 is 4. 4 meters per second divided by 2 is 2 meters per second times 10 seconds. 5 seconds gives me 10 meters. So this is going to be 10 meters when I plug in these values. This is V naught. This is the final velocity. This is the time. Plug it all in, you get 10 meters. But really what this is here's another way of looking at it. Look at the third kinematic equation. V naught t plus 1/2 a t squared. Is that okay? Sure, because what's the acceleration? 0. So this whole term vanishes. And so it's the initial velocity times time. Now this is the one that I really want to examine, because look at this. Here's what I'm saying. I'm saying I have a quantity, displacement, that is equal to the product of these two quantities. That is my velocity, my constant velocity, times time. Super profound idea right now. So listen, we're going to use this idea over and over and over again. Whenever I've got a quantity that is the product of two other quantities, if I graph this one as a function of this one, the area underneath that graph will give me the third one. So this quantity times this quantity. Well, what is this times this? This is like the height times the width. The height times the width. So the height of this is, 2 meters per second, and the width is 10 seconds. So that's, 5 seconds. I'm sorry. 5 seconds, and that gives me 10 meters. Okay? Then we extended this idea to go a situation where the velocity doesn't stay constant. What if I had a graph that looked something like this? 1, 2, 3, 4, 5. Time in seconds. Maybe this is so we'll start here. Something like this. So 2, 4, 6, and this is velocity in meters per second. And so now I can still find the total displacement of the object. So its final velocity is 6. Its initial velocity was 2. It's so how far did it go? What's the displacement? Well, the displacement is again, just like it is up here, the displacement is just going to be the area underneath that graph. It's just that now the shape is a little different. Now last time we called it a trapezoid, and we came up with this second kinematic equation. But you can also look at it as a rectangle and a triangle. So let's do that. And here's a triangle. So the rectangle, we'll call this delta x1, and this is delta x2. This is the displacement due to my initial velocity. This is the displacement due to my acceleration. And so, well, what is delta x1? Well, that's going to be equal to v naught. We'll call this v naught is 2 times time. Okay? Now, what is delta x2? Well, delta x2, and then we can plug in the numbers here. What is v naught times t? It's 2 meters per second times 5 seconds. So that is 10 meters. Now delta x2, this is a triangle. And what's the area of a triangle? It's 1/2 the base times the height. So that's 1/2 the base, we'll just call it t. And what is the height? Well, the height is from here to here. This is my final velocity, and this is v naught, so it's the difference between those two. And that gives me the area of the triangle here. And so if I plug that in, I get the 1/2 times t, which is 5 seconds, times v, which was 6 meters per second, minus my initial v, which was 2. Off screen, sorry. So what does that equal to? That's 6 minus 2 is 4. 4 divided by 2 is 2. 2 times, oh, it's 10 meters again. I didn't mean for that to happen, it just did. So it's 10 plus 10 is 20 meters. That's my total displacement. But I want to look at this a little bit. I want to massage this. I want to show you something kind of clever. This is a straight line equation, right? I mean, we can say v equals the slope, which is the acceleration, times time plus v naught. So what I'm going to do is I'm going to substitute this in here, and I'm going to say delta x2 is equal to 1/2 of t times at plus v naught minus v naught. Well, what is delta x2 equal to then? Just generally. Well, what is v naught minus v naught? 0. So that stuff goes away. So I've got 1/2 t times at. What is that? Well, that's 1/2 a t squared, which we've seen before. Right? If we have, so we can say delta x, the total displacement underneath this graph, is equal to delta x1, which is v naught times t, plus the area of this triangle, which can be expressed as 1/2 a t squared. And that's the third kinematic equation, derived in a slightly different way than we did last time. And so whenever you see this third kinematic equation, if you have a situation where the acceleration is constant, you can say, okay, look, this right here tells me how much I changed my position because I had some initial velocity. And this tells me how much I changed my position because I'm changing my velocity at a constant rate. This is my displacement due to acceleration. This is my displacement due to my initial velocity. Make sense? It's kind of cool that we can derive these equations in different ways. Okay, now before we get any farther, I want to say this. This idea of finding a quantity, in this case my displacement, by finding the area underneath a graph, either all at once or by dividing it up into shapes, is called integration. Okay, and you know, people spend years studying all kinds of different techniques for how to do integration. Okay, but this is what it is. Now, one of the things that you're going to be able to do in this class is if I give you a velocity versus time graph, you can figure out what the displacement is by just drawing triangles and rectangles or trapezoids or whatever and figuring out the area underneath the graph, and you'll get your answer and it'll be perfect. And that'll be good. Okay? But now, but sometimes you're going to get stuff that looks like this. Suppose I've got a velocity versus time graph that doesn't have constant acceleration, where the acceleration varies with time. Okay, so in that case, maybe we'll make this the initial velocity. It might be a nice curvy shape like that. Okay, so if it's a curvy shape, okay, then, and you want to find what's the displacement, let's say start from t equals 0 to t equals, I don't know, 3 seconds or something like that. What you're going to do now is you're going to find the area underneath the graph, like this. Well, how do you do that? Well, what you can do is you can break it up into chunks and add them together and get an approximation for what the area is underneath the graph. So let's break it up into chunks. Well, now there's various ways to do it. Let's just go like maybe every second. 1, 2, and you go, oh geez, all right. Well, how do I figure out this area? Well, it's kind of like a trapezoid, so maybe I can figure that out. And this, I don't know. This, well, I'm too lazy. I don't want to deal with trapezoids and triangles, okay? I've had it with trapezoids and triangles. I only like rectangles. I'm a rectangular kind of guy. So here's my final, so here's my initial time, my time. So what I'm going to do is I'm going to break this up into rectangles. And so I'll figure out what the area of this rectangle is, what the area of this rectangle is, what the area of this rectangle is. I'll add them up and I'll come up with an approximation. And you see that that approximation is terrible. But I don't care, it's good enough. All right. Well, what if it isn't good enough? Well, see, look, I'm missing all this area, and I'm missing all this, and I'm missing all this. I know, let's break it up into more rectangles. So that's what I'm going to do. So I have this rectangle, and now my rectangles are all supposed to be the same size, but oh well. And here's what I've done. Notice that when I add up, the area of this rectangle and this rectangle, I'm including some of this stuff I didn't include before. I have less error. Okay? And so now I can see I missed that, missed that, missed that, missed that, missed that, missed that, missed that. So I'm still missing a little bit of area, but not nearly as much. Well, maybe that's too much area I've missed, so what am I going to do? I'm going to cut it up into more rectangles. And basically what you do this is you keep cutting this up into more and more rectangles until you die. Because you're going to do this forever. What you do is you cut it up into rectangles forever. Basically what you're going to do. Now, the width of these rectangles, right here, we call this delta t. And so what we're going to do is we're going to do this. We're going to, here's a little rectangle, and it has a height, we're going to call it v times delta t. And we'll call this vi. And then we'll say, okay, here's this, and I equals 1 to n, and we're going to add them all up. Okay, we're just going to add from here all the way over to here. But then what I'm going to do is, and by the way, you're getting like several weeks of math like in one little lecture. But I think it's doable. You just have to be patient with yourself. It's going to take a while. I'm going to break this up into so many rectangles. Let's take the limit of this as delta t goes to 0. We're going to let delta t go to 0. Well, what does that do to my number of rectangles if delta t goes to 0? It becomes infinite. So what happens is that I get a little infinitesimal slice here. Let's take a look at it. Infinitesimal slice. Now, by the way, an infinitesimal slice of this area is infinitely small. It has infinitely small area. Okay? But it is a rectangle, and when you let delta t shrink to 0, we call it dt. That's what dt means. It means, hey, it's infinitesimal. It's delta t shrinking to 0. It is not 0, but it is shrinking to 0. And this, well, this is v of t, right? whatever, at this is at some time t, and then you do that. And so what you can do is say, well, what this gives me is an infinitely tiny amount of displacement. Now, an infinitely small amount of displacement is dx. Now remember, x here is not the x-axis. It's a small amount of displacement. We're using x to represent displacement. That is, this is the tiniest little change in position you can imagine. And what it is, it's my velocity time as a function of time times a little tiny bit of time, right? Velocity times time is displacement. Well, if you have your velocity and you multiply it by the tiniest little bit of time, you have changed your position by a little tiny bit. This is a tiny bit of displacement is equal to your velocity times a tiny bit of time. And when I say tiny, I mean as tiny as you can get. Well, so I've got billions and billions, well, trillions, well, an infinite number actually, of these infinitesimal slices. What am I going to do to all those slices? I'm going to add them all up. And what's a great word for add them all up? There's one word, sum. Sum, right? Or I should say sum. Sum. I'm going to sum up all of my little dx's, all my little tiny displacements, and when I sum all my little displacements, I get all of my displacement. I get the total displacement. Well, to do that, I have to sum all of my little products between velocity as a function of time times time. Now, here's one. Oh, oops, sorry. Tell me if I'm off screen. This is a product, folks. A product of velocity and time. Velocity times time gives me displacement. But when I add them all up. I add up all these little tiny products up to get my total answer. That's what you're doing when you're doing integration. Those of you who've already had integration, this is what it means. This is what you're doing. It's the way you handle a product when the velocity, when you're trying to multiply velocity times time, but your velocity depends on time, your velocity is changing with time, that's when you have to use this amazing mathematical technique called integration. Okay, but this is why you're doing it. Okay, well, we have a whole bunch of rules for integration. And you have to learn those rules, and you just have to follow them. And I'm not going to tell you how these rules are derived. You have to believe me that it works. And you have to take a really great calculus class and derive them all in your math class, because that's what you do in a math class. Because, that's what you're going to do. Well, let's take a function that I already know. Well, first let's go over the most important rule. And that is, it's called the power rule. Okay? And so in the power rule, of integration, let's say your velocity as a function of time is some kind of polynomial. So let's say that it's the acceleration, or not acceleration, I'm sorry, let me use a different letter for this, because A means acceleration in physics. So let me just use, I'll use B. And what is that? That's just some constant. Just some constant goes out in front. T, right? Velocity is a function of time to the n power. Okay? Well, what are we going to do to figure out displacement here? We're going to remember that displacement, a little tiny bit of displacement, is going to be equal to velocity times a little bit of time. Okay, now let's take a look at this qualitatively, folks, okay? What I'm doing is I'm taking something, let's go b times t to the n. Look what I'm doing here. I'm really multiplying it by time. Now, it's a little tiny chunk of time, but let's just look at the units here. I'm multiplying it by time, I'll put it in quotes, again. If I take time, well, look, if I take time and then I multiply it by time again, what is this? This is t squared, right? What if I have t to the n times time? What does that equal to? T to the n plus 1. And that's really what you're doing here. You're taking some function of time and you're multiplying it by time again. So what are you going to do to the exponent? You're going to add 1 to it. That's what's going on. So in the power rule, when you say the integral of a to the t n times dt, right? See, really, this is kind of like my velocity, and this is time. What you get is you keep the a. Oh, I'm sorry. I was going to use b, wasn't I? Yeah. Because I don't want to confuse it with acceleration. Sometimes it is acceleration, but I don't want to confuse it for acceleration. It's b, and then times time, t to the n times time is t to the n plus 1. And then what do? Folks that have already had calculus. You divide it by the new exponent, right? You divide it by n plus 1. Now, those of you who haven't had calculus yet, you just need to accept that on faith right now. You'll derive it in your calculus classes. I'm not going to do it. You know why? Because I don't remember how to do it. Okay? But I don't need to because I'm a physicist. All right, so, I think I did. I did for a while because I taught AMA for a couple years. And then I didn't last year, and so it's gone. All right, but I can relearn it easily enough. All right, so there's a whole bunch of these integrals, okay, and you have to learn the rules. Now, where did I put my book? Now, the book uses x instead of t. I like to use t for time because that's what we use as physicists. But if you open your book to this, whoops, not that far. Integral calculus, A25. Let's zoom out. Actually, I'm going to zoom back in here. They have this little table here. And oh wait, those are the derivatives. Oh, here it is. They have this table here. And let me zoom in so you can at least sort of, maybe some of you can see it, and that's okay. This is on page A.27 of your book. And they have all these integrals. X to the n dx is x to the n plus 1 over n plus 1. That's the power rule. That's the one you're going to use the most. Okay? So you're going to have to read this. Now, there's one other thing that you need to know, and I'm running out of time. Speaking of time, 9:51. Okay. Oh, a little more time, I thought. If you just do this is called an indefinite integral. And of course, those of you who've had calculus already, you know you have to add plus c to the this. If you haven't had calculus yet, don't worry too much about that because we don't do that in here. We use what's called definite integrals. So let me go back to this here. When I want to find out what delta x is here, what delta x is, I need to say, okay, from when to when? Okay, When are you going to start and when are you going to end? Now, we have a way of writing it down. This is just where we chose to write it down in the equation. When you have an integral like this, you want to say, okay, when does your time start? What is your initial time? So I'll call that t initial. And what is your final time? We'll call that t final. Now, to find out delta x, right, you need to know what is your, what is x final minus x initial, right? That's delta x is x final minus x initial. Well, how do you find your x final? You plug in your t final. And then how do you find x initial? You plug in your t initial. And then you subtract them, right? Delta x is x final minus x initial. So when you, I'll tell you what, let me just do this by an example, because an example will work way better than an abstraction. Yeah, 3. I'm going to use that. I'm going to use this, well, no, I'm going to use 5. I'm going to use 5. Why? Because we've already done it. I'm basically going to do this problem right here. I'm going to do this problem because it's super easy. All right. And so I'm going to say, all right, here's an example of how do you do this with integration now. Let's suppose that my velocity as a function of time is equal to what was the acceleration there? Oh, let's go back to this. This v was 6, this was 2, so this is 4 meters per second divided by 5 seconds, right? So that's 0.8. 0.8 meters per second squared. Yeah, it would be nice to have a nice round number, but who cares? Times time, plus my initial velocity was 2 meters per second. So this is my velocity as a function of time. And I want to know what is my displacement at t equals 5 seconds. So I want to find, this is what's given. I want to find delta x at t equals 5 seconds. Well, of course, you would use the kinematic equations to do this, or you would graph it and figure out the area underneath this. But instead, we're going to do it a totally impractical way. We're going to use a definite integral to do it. So let's solve. So I'm going to say delta x is equal to the integral of velocity as a function of time times our little chunks of time, and we're going to sum it from 0 to 5 seconds. See, my time, my delta t, this is my delta t, the initial delta t, or the initial time is 0, the final time is 5 seconds. Yes? Now what I'm going to do is plug in my equation, 0.8 meters per second times time plus 2 meters per second, and I'm going to multiply all of that by dt. Then, now I'm going to apply the power rule to this. And the power rule, as we just said, is this ugly thing right here. This. And so I'm going to say, well, this is my b for this one. And I'm going to say b is 0.8 meters per second squared, sorry, times time. But what is time times time? Time squared, but then you have to remember to divide by 2. So this is my expression for delta x. But then I have to worry about this, plus, now 2 meters per second, that's kind of like 2 meters per second, oh, got it, keep getting off screen, times t to the 0 power, right? Well, I'm going to apply the power rule to that. So this is my 2 meters per second times t to the 0 times t. What is 0 plus 1? It's t to the 1 power divided by 1. But I don't put that. I'm done. Now, this is my delta x. But in order to figure out delta x, I need to know my, my final minus my initial. So here's how we show that. I usually put this in parentheses, and then I go like this. A little line like this, and this is just notation. Hey, I'm going to apply, here's my initial time, and here's my final time. Now I'm going to plug these in here. So delta x equals, what is x final? Plug the final time in, and you'll get x final. Well, what is, this is 20.8 meters per second squared times, let's see, 5 times 5 is 25 seconds squared divided by 2. Okay, plus, plug your 5 in there, 2 meters per second times 5 is 10. 10 meters. Okay, now that's my, this right here is my final position. Now, minus my initial position, well, my initial position happens at my initial time, which is 0. What happens when I plug in 0, both of these? They're both 0. And so now I get delta x. Well, let's see, that's 0.4. 0.4 times 25 is 10. 10 meters plus 10 meters, 20 meters. And that was the answer that we got 2 different ways before. Okay, so this is a lot. This is a lot. I'm not sure this lecture is complete enough to allow you to solve integrals, but we're going to give it a shot. I'm going to show you the worksheet that I want you to do. And again, I forgot to make copies of it, so here I'm just going to blow this thing up. And when you can look it up on YouTube. And when you look it up on YouTube, you can just freeze it right there, and then you know what the assignment is. Also, I will make this worksheet a document that you can get on it. And I'll tell you what, because I'm not giving you the worksheet today, I won't make it due on Tuesday, but you would be wise to work on it as much as you can over the weekend, especially those of you new to calculus. Okay, so that is all.